Morning students. Today we discuss partial differential equation. Here we look some definition of partial differential equation, what is the order and degree of partial differential equation, and further classification of partial differential equation and formation of partial differential equation. So first, what is partial differential equation? A differential equation which contains partial order derivative is known as partial differential equation. Here, the differential equation contains partial differential coefficient of some function, and that function is a function of two or more variable. That function is a function of two or more variable. Then such type of equation which contains partial derivatives is known as partial differential equation. Now, what is order and degree of partial differential equation? So, if a partial differential equation PD contains nth order and lower order derivative, it is said to be of nth order partial differential equation. It means any partial differential equation which contains highest order derivative. The highest order derivative is the order of that partial differential equation. And what is degree of partial differential equation? The greatest exponent of highest order derivative is degree of partial differential equation. Further we look when a partial differential equation becomes linear. If it is of first degree in dependent variable and its derivative. Suppose we have a partial differential equation in dependent variable z and independent variable x and y. Then this equation will be linear if it contains only terms of z in first degree and only terms of its derivative in first degree, and their product must not be present there. So power and product of dependent variable and its derivative must absent. Power and product of dependent variable and its derivative must be absent, then a partial differential equation becomes linear. Now there are some examples of partial differential equation. The first is del 2u upon del x square plus 1 plus cos u del 3u upon del x square del t is equals to 0. This is a partial differential equation in dependent variable u and independent variable x and t. And highest order derivative term is del 3u upon del x square del t. So the order of differential equation will be 3, and the exponent of this term is 1. So its degree will be 1. It's a third order non-linear partial differential equation with degree 1. Non-linear because dependent variable cos u is present here with with product del 3u upon del x square del t. That's why it will become a non-linear partial differential equation. In second example, del 2u upon del t square plus 2 del 2u upon del x square plus u is equals to t. Here again dependent variable is u, independent variables are x and t, and highest order derivative term is del 2u upon del t square as well as del 2u upon del x square. So it is a second order partial differential equation, and its degree here greatest exponent of second order term is 1. So its degree is 1, and it's a linear partial differential equation because exponent of dependent variable is 1 everywhere, exponent of derivative is 1, and nowhere their product exists here. In next example, del u upon del t plus twice 1 plus x square del 3 u upon del x cube plus u is equals to t. Here u is dependent variable, x and t are independent variable, and this is a third order partial differential equation, and it's again a linear partial differential equation because the exponent of derivatives and dependent variable is 1, and their product is absent here. Now we look classification of first order partial differential equation. These can be divided into some types like linear, semi-linear, quasi-linear and non-linear. So we have already seen when an equation will be linear if the power and product of dependent variable and its derivative must be absent. A first order partial differential equation become linear. And in what case it will be semi-linear? Suppose we have a partial differential equation of the form a function of x, y, z pq equals to 0, where z is some function of x, y. It will be a semi-linear if it is linear in p and q. Also the coefficient of p and q are some function of x, y only, not of z. Suppose we have an equation like p plus q equals to r. In this equation, small p and small q are del z upon del x and del z upon del y. These are standard notation. Here z is dependent variable, x and y are independent variable. So small p denotes del z upon del x, first order partial derivative of z with respect to x, and small q represent del z upon del y, first order partial derivative of z with respect to y. Here p, q and r, these are some function of x, y and z. So now we classify semi-linear, quasi-linear and linear on behalf of capital P, Q and R. Suppose if capital P, Q and R, these all three are function of x, y only, capital P, capital Q and capital R, these all three are some function of x, y only, this equation becomes a linear equation. Whereas if capital P and capital Q are function of x, y, but this R may be some function of z, may be some function of x, y and z, it becomes semi-linear. But capital P and capital Q are function of x, y only, not the function of z. So in definition of semi-linear, it is a linear in P and Q, also the coefficient of P and Q are function of x, y only, not of z. So this will become semi-linear if capital P and capital Q are some function of x, y only. Now we look quasi-linear. Suppose again this equation will become quasi-linear if this capital P and capital Q, either of each or both are some function of x, y and z, then it becomes a quasi-linear equation. And non-linear, which doesn't come under these conditions, will be a non-linear equation. Now we will look formation of partial differential equation. We can derive a partial differential equation from a given equation which is capital Fxyz, function of Fxyz AB equals to 0. From this equation we can derive a partial differential equation by eliminating arbitrary constant a and b. So if we are given such type of equation, we are to eliminate a and b and we get required partial differential equation. To eliminate a and b, first we differentiate this given equation 1 with respect to x and y partially. Here the important thing is that this z is function of x, y. Z is dependent variable, x and y are independent variable. This z is function of x, y. So when we differentiate f with respect to x, first we differentiate f with respect to x as well as we differentiate f with respect to z, then further we differentiate z with respect to x. So when we differentiate this with respect to x, we get del f upon del x plus p del f upon del z equals to 0 using total derivative. Similarly, when we differentiate 1 with respect to y, we get del f upon del y plus q del f upon del z is equals to 0, where p is what? Del z upon del x and q is del z upon del y. Now, using these three equations, first equation number 1 and in 2 we have two equations. From these three equations we eliminate a and b, and resultant equation will be a function of x, y, z and pq. This resultant equation will be a first order partial differential equation. And if in the equation 1 number of arbitrary constant, which are a, b here, number of arbitrary constant are more than variable, more than the number of variable, the order of partial differential equation become higher. If there are more arbitrary constant than independent variable, then the above procedure of elimination results into partial differential equation of higher order than first. Now we look some example. Suppose we have an equation z is equals to ax plus by plus a square plus b square. We are to derive a partial differential equation from this given equation. Here a and b are arbitrary constant, and to derive partial differential equation we are to eliminate a and b. To eliminate a and b, first we differentiate z with respect to x and with respect to y partially. So when we differentiate this equation with respect to x, we get del z upon del x in left hand part is equals to a. Del x over del x become 1. So here we have a plus 0 plus 2a, sorry 2a not, because a square is arbitrary constant, it becomes 0, b square again arbitrary constant, it becomes 0. So del z upon del x is equals to a. Similarly, when we differentiate 1 with respect to y partially, we get del z upon del y is equals to, it becomes 0, it gives b plus 0. So del z upon del y is equals to b and del z upon del x is equals to a. Del z upon del x is equals to p. So we have p equals to a, and del z upon del y is equals to q. So q equals to b. Now using 1 and 2 we eliminate a and b. So we get a is equals to p and b is equals to q. Putting the value of a and b in equation 1, we get z is equals to px. In place of a we put p, and in place of b we put q. So it becomes z is equals to px plus qy plus p square plus q square. So required first order partial differential equation is z is equals to px plus qy plus p square plus q square, where p is del z upon del x and q is del z upon del y. Now look some another example. Find the differential equation of all sphere of radius lambda having center in the xy plane. Now all sphere of radius lambda. What is the equation of such type of sphere? This is a family of a sphere. Then equation of such type of sphere is x minus h whole square plus y minus k whole square plus z square is equals to lambda square. Here the radius of the such type of sphere is constant, which is lambda, and second thing, their center lie in xy plane. So in xy plane z coordinate become 0, or coordinate of center become 0. So center coordinate might be hk0. So we have equation x minus h whole square plus y minus k whole square plus z square is equals to lambda square. In this equation, h and k are arbitrary constant. Here lambda is also constant, but it's not an arbitrary constant, it's already given. So arbitrary constants are only two here, which are h and k. So to find partial differential equation, we are to differentiate this equation 1 with respect to x and y partially. we get, when we differentiate this with respect to x, we get twice x minus h plus 0 plus 2z, as z is function of x and y. So we differentiate z with respect to x, so it gives 2z del z upon del x is equals to 0, as lambda is constant. So first twice x minus h plus twice z del z upon del x is equals to 0, or we can write it like x minus h is equals to minus z del z upon del x. Now when we differentiate 1 with respect to y partially, we get this, it gives 0, it gives twice y minus k plus twice z del z upon del y, as z is function of y also, equals to 0. So we get y minus k is equals to minus z del z upon del y. Now we are to eliminate h and k from equation 1 and 2. So here we have a term x minus h and y minus k, and we have the value of x minus h is equals to minus z del z upon del x, and y minus k is given by minus z del z upon del y. So in equation 1, replace x minus h with minus z del z upon del x, and y minus k replace with minus z del z upon del y. So it becomes minus z del z upon del x whole square plus minus z del z upon del y whole square plus z square equals to lambda square. When we simplify this, we get z square 1 plus p square plus q square equals to lambda square, which is required partial differential equation. Now another example we have, find the differential equation of the set of all right circular cones whose axis coincide with z-axis. So first we look the general equation of right circular cone whose axis coincide with z-axis. So its general equation, suppose the axis coincide with z-axis and let the semi-vertical angle is alpha. Semi-vertical angle is alpha and vertex is 0, 0, C. So general equation of right circular cone is given by x square plus y square equals to z minus c whole square tan square alpha. Here c and alpha are arbitrary constant, and to eliminate c and alpha, we are to differentiate this equation with respect to x and y. So when we differentiate it with respect to x, we get 2x is equals to 2z minus c tan square alpha del z upon del x. Similarly, when we differentiate 1 with respect to y, we get 2y twice z minus c tan square alpha del z upon del y. Now here z minus c, now multiply 2 by y and 3 by x, we get 2xy is equals to this term into y, and when we multiply 3 with x, we get 2xy equals to this term multiplied by x. Here in left hand side, both part are xy, so both part are same, so right hand part must be same. It gives us z minus cx tan square alpha del z upon del x is equals to z minus cy tan square alpha del z upon del y. When we simplify it, this tan square cancel out, z minus c cancel out, so resultant equation becomes x del z upon del x is equals to y del z upon del y, which is required partial differential equation. So it's a one type to format partial differential equation. In next lesson we look another way to formation of partial differential equation. Okay, thank you.